Dalton's law of partial pressure. John Dalton stated that for a mixture of gases, the total pressure is equal to the sum of the partial pressures exerted by each gas. Partial pressure is the pressure of each gas in a mixture. It's the pressure that the gas would exert if it were by itself in the container. Dalton's law of partial pressure indicates that pressure depends on the total number of gas particles and not the type of gas particles. That's because, according to the kinetic molecular theory, there are no attractive or repulsive forces between gas particles. The total pressure exerted by a mixture of gases is equal to the sum of the partial pressures of those gases. P total is equal to the partial pressure exerted by gas 1 plus the partial pressure exerted by gas 2 plus the partial pressure exerted by gas 3. Since we assume that the gas particles do not interact with one another, the pressure exerted by the gas, whether a single pure gas or a mixture of gases, that pressure is determined by the total number of gas particles and not the identity of the gas particles. For a mixture of ideal gases in a container, the total pressure is equal to the sum of the partial pressures. Let's see if you can determine what the total pressure will be when we combine oxygen exerting a pressure of 200 torr with nitrogen exerting a pressure of 330 torr. Combining them in an equal size container at the same temperature, what will be the total pressure? 200 plus 330. That's right. The total pressure will be 530 torr. In this mixture, oxygen is exerting a partial pressure of 200 torr, nitrogen is exerting a partial pressure of 330 torr, for a total pressure of 530 torr. At STP, 1 mole of a pure gas occupies 22.4 liters. Likewise, 1 mole of a gas mixture also occupies 22.4 liters. So if you look at the container on the left, 1 mole of nitrogen at STP, it occupies a volume of 22.4 liters. The middle container, composed of 2 different gas particles, oxygen and helium, with 1 mole of gas total in the container. At STP, even though this is a mixture of gases, it also will occupy 22.4 liters. And the last container, composed of 3 different gas particles, oxygen, helium, and argon, 1 mole total. At STP, you should know what the volume will be, 22.4 liters. Mole fraction and partial pressure. The partial pressure of each gas is equal to the mole fraction, symbolized by Greek letter chi, of each gas multiplied by the total pressure. The mole fraction is the number of moles of one component of a mixture divided by the total number of moles of all gases present in the mixture. The formula: moles of gas A divided by total moles of gas that would be the mole fraction of gas A. You multiply the mole fraction times the total pressure to get the partial pressure of gas A. Mole fraction is like a percent. If you look at this diagram, you see that 3/12 of the gas particles are yellow. 3/12 is 0.25, or 25% of the gas particles are yellow. What does that mean? That means that 25% of the total pressure in this container is caused by the yellow gas. The mole fraction of the red gas is 9/12, or 0.75, or 75% of the gas particles are red. What does that mean? It means that 75% of the total pressure in this container is caused by the red gas particles. The mole fraction of A plus the mole fraction of B plus the mole fraction of C equals 1. If you add up the mole fractions of all the component gas particles in a mixture, it will equal 1. The partial pressure of any gas, say A, in a mixture is given by partial pressure of A is equal to the mole fraction of A times the total pressure. Let's look at a problem. A mixture of helium, neon, and argon gases have a total pressure of 790 millimeters of mercury. If this mixture is made up of 15% argon, 60% helium, and 25% neon, what is the partial pressure of each gas? In order to solve this, we're going to look at this formula. P total is equal to the partial pressure of helium plus the partial pressure of neon plus the partial pressure of argon to equal 790 millimeters of mercury. Now all we have to do is look at the percentages. 15% of 790, 60% of 790, 25% of 790. To find the partial pressures, you take the percent, which can also be found by using the mole fraction, and you multiply it by the total pressure. Let's consider one more problem. If the total pressure exerted by the gas mixture is 780 millimeters of mercury, calculate the partial pressures of gas A and gas B. We're going to take gas A, combine it with gas B in a same size container at the same temperature, and let's see if we can determine the partial pressures of gas A and gas B. Step 1. Determine the number of moles of each gas. Well, let's say that each sphere represents a mole of gas. That means there are 6 moles of gas A and 10 moles of gas B. Step 2. Determine the total number of moles of gas. Well, that's easy. You're just going to add 6 plus 10 to get 16 moles of gas mixture. Step 3. Make a mole fraction for each gas. For gas A, it would be 6 over 16, and for gas B, 10 over 16. And finally, we're going to use the formula. The partial pressure of some component, I, is equal to the mole fraction of that component times the total pressure. In other words, we're going to take 616 times 780, which means that component A exerts a partial pressure of 292.5 millimeters of mercury. Component B has a mole fraction of 10/16 times the total pressure of 780 to give us a partial pressure of 487.5 millimeters of mercury. You can always check your work because the sum of the partial pressures should always be equal to the total pressure, and the sum of the mole fractions should always equal 1. 292.5 plus 487.5 equals 780 millimeters of mercury, the total pressure. 6/16 plus 10/16 is equal to 16/16, or 1.